We are very pleased to have Joé Brendel from Tel-Aviv University, who will tell us about local exotic tori.
Okay, thank you very much. Thanks for being here. Thank you to the organizers. Yeah, so this is something I've been working on for a while now, and I'm currently writing up the paper, so it should be on the archive soon. Where I want to find soon to well, so we'll see. Let me give an outline of what I want to talk about. So first, before talking about the results themselves that I'm interested in today, I will give a sort of brief overview of exotic Lagrangian tori. So sort of what is known and what is still open, and where the results that I'm going to talk about will fit into the story. And then the sort of the meat of the talk will be these 3 paragraphs here, where I will give a construction of exotic tori in this is something that will happen in C3. And then use versatile deformations as an invariant together with displacement energy to distinguish the tori. And then I will see what happens to those tori, or we'll discuss what happens to those tori if you take them in a Darboux chart in a tame symplectic manifold, and we'll discuss a bit what happens to the image of such an embedding. And then if I have time, which may not be the case, I will talk about further questions and further directions of research related to this this story. Okay, so let's give a quick overview. So as we probably all know, a Lagrangian submanifold of a symplectic manifold is just something which is half the dimension of the ambient space, and on which the symplectic form vanishes. And today I won't talk much about other Lagrangian submanifolds than tori, so you can mostly think of tori for today. And sort of an ambitious question would be, so you take a certain say you fix a certain diffeomorphism type maybe, or certain Lagrangian up to Lagrangian isotopy, and you ask for a classification of this Lagrangian up to symplectomorphisms. So maybe you want to know what are all of the Lagrangian tori in R4, and we'll see that for this problem, for example, it's still open. So that's why I call this goal kind of ambitious. Except for the case of surfaces. So in the case of surfaces, it's a bit less ambitious, because then you get away with just doing area arguments. So for example, take R2 and just take a closed embedded curve. Any closed embedded curve. So if we take a curve that lies here somewhere, will be Hamiltonian isotopic to just a standard circle of a certain radius. The only thing you need to check is that sort of the area here enclosed by the curve is the same as the area enclosed by the circle here, because Hamiltonian isotopies in the plane are the same as area preserving isotopies. And yeah, so I'll denote for the rest of the talk, I'll denote these standard circles enclosing a certain area A by S1A. Okay, so A is the area here enclosed by the circle. And then sort of natural next question you can ask, so what's the next thing you can do? Well, you can take products of this example, right? So now take a product of 2 copies of the plane, you end up with R4, and take a product of the circles, which will give you so-called product torus. And I will denote them by T, and then in the parentheses 2 parameters, which are the 2 area parameters of the corresponding circles. Sometimes they're also called split tori because they sort of split into the factors of the ambient space. I will call them product tori. And then a natural question. So with respect to this discussion in the surface case, a natural question would be, given a Lagrangian torus inside of R4, is it always true that it is equivalent? So either take Hamiltonian diffeomorphisms or Symplectic dimorphisms, here it doesn't matter, to a product torus. Okay, so here I mean, let's say, for simplicity, say Hamiltonian diffeomorphisms. So are there other tori besides those sort of standard ones? And the answer to that is yes. So Chekhanov has produced the first example in 96. So this is nowadays called the Chekhanov torus, and I will denote it by TCH of A. So A is again some sort of area parameter. They come in, they come in a one parametric family, which is essentially scaling. In C2, you can scale somehow. And this will be my notation for those Chekhanov tori in C2. And he, as invariants, he used versatile deformations, which is the invariant that I will be using today also. And simultaneously, Eliashberg and Poltorovich gave a different description of the same, or of a torus that turns out to be Hamiltonian isotopic to the Chekhanov torus. And they used another invariant, namely count of J-holomorphic disks with boundary on L to distinguish the Chekhanov torus from the product tori. And actually, my talk will be kind of a mix of the two, so that's why I mentioned the 2 papers, because the construction of the tori that I will give is very much inspired by the construction Eliashberg and Poltorovich gave, whereas my method for distinguishing them will be Chekhanov's original method by versatile deformations. And so what does this exotic mean? By exotic, I just mean a torus that's not, so for example, the Chekhanov torus, a torus that's not equivalent to one of the product tori. And somehow in C2, we still don't know the classification of the Lagrangian tori. We just know that there's one more example given by this Chekhanov torus, but as of now, it's unknown whether there's maybe a third torus or a third family of monotone tori inside of C2. There's been some progress made under some topological assumptions on the tori by Dimitroglou and Frizel, but it's not known whether you can drop sort of topological assumptions. So the question is still open. And so something a bit more humble you can try to do instead of pursuing this classification is just, well, try to come up with new examples and play around and see what is possible somehow. And I'd like to mention a few papers in that regard. The first paper being one by Chekhanov and Schlenk, where they produce other exotic tori in products of S2 and CPN. So there, of course, my definition of exotic doesn't work so well anymore because we're not in CN anymore, but there's a natural sort of analog of product tori, which both of these spaces have a toric structure, so you can say, well, I want tori that don't appear as fibers of a toric moment map, for example. And this was also done using versatile deformations. And then the big sort of breakthrough papers, I guess, were by Oro and by Viana. So Oro proved that there are infinitely many monotone tori in C3. So in C2, as I said, this is still open, but in C3 at least, there's not only the product and Chekanov, you can find infinitely many more. And Viana proved the same thing for CP2, so an example of a four-dimensional ambient space where you can find infinitely many. And then later on generalize it to other Del Pezzo surfaces, so S2 times S2, blow-ups, and so on. Right. And there are, so as a remark, most of the tori that were studied are monotone, meaning that the Maslov and the area classes are positively proportional. An exception is a paper by Shelochin, Tonkonok, and Viana, where they sort of distinguish non-monotone sort of Viana tori in CP2. These can also be detected by versatile formations, and somehow I forgot to change the slides, but I noticed that there's another example actually in S2 times S2. There's also a paper by FO cubed. So in S2 times S2, you also have non-monotone exotic tori. And so why am I talking about this monotonicity stuff? Well, one of the main points of the talk today that I'd like to sort of advocate or somehow discuss is that the versatile deformations are very nice to treat non-monotone tori. So you don't need to actually adapt anything or say anything more than in the monotone case. You can take the invariant as such and apply it also to the non-monotone case. And this will come up like this will be very important for the rest of the talk, that you don't have this monotonicity condition. So okay, so let's move on maybe to the main results that I want to talk about. So in the talk I'll focus on dimension 6, but everything I say applies to higher dimensions as well. So everything beyond 6. The point being that it's really 6 and onwards. Like I won't say anything about dimension 4 in this talk. Right, and the objects I will be interested in come in a accountably infinite family. So I take a k in this set here, integers bigger or equal to -1. We'll see later why I start at -1 and not at 0. And the tori come in 2-parameter families. So the A1 and A2 will be my parameters. They will be strictly positive numbers. And for each k, for each A1 and A2, I get a Lagrangian torus in C3, which have the following property. If I change the k, so if for k and k prime, I look at tori having the same parameters. So you should think of those parameters as sort of area classes in some sense. If they have the same parameters, then they have the same area and Maslov class. So they are not distinguishable by sort of classical invariants in some sense. And it's even slightly stronger. You can show that they are Lagrangian isotopic, and you can choose the Lagrangian isotopy to be arbitrarily small in terms of flux. Which implies in particular what I wrote here. But this means that they are as close as they can get without being Hamiltonian isotopic. And so the theorem is, indeed, they are not. If you take different k and k prime, whichever member of the two-parametric family you look at, they will not be Hamiltonian isotopic and not be symplectomorphic. It will be different tori. So this is the result in C3. Some remarks are that those tori are not all monotone, but there is a one parametric subfamily of monotone tori. If you set one of the parameters, this is a choice, but you set one of the parameters equal to 0, you get a subfamily of monotone ones, which means that in particular we would reproduce Aarhus result about this infinitely many tori. But the construct, so other than the result itself, it's completely disjoint. So the construction as well as the way we distinguish them is different from Aarhus. And to be honest, I don't even know if the tori that we construct are the same as Aarhus tori. So I haven't. It's at least not obvious. So you'd have to do some work. This I actually don't know. Okay. And then the second part of so this is the first main result. It's slightly stronger than Aarhus because you have these non-monotone guys, right? But it's essentially Aarhus result. But the second one is new to my knowledge, and the second thing is about so whichever ball you take in C3, it will contain members of these two parametric families if you take the parameters small enough. And so you can ask, I take a Darboux chart going from an embedding of the ball into a tame 6-dimensional symplectic manifold. And then you can ask, are those tori still distinct inside the new ambient space? Which is not obvious. I mean, because you add a lot of topology, you had a lot of topology and symplectic topologies. You may think that there's some symplectic isotopy going through the bigger ambient space and coming back to your double embedding and sort of mapping the one torus to the other. And the claim is that if you choose the tori small enough in this Darboux chart, then this does not happen. So the tori are still different for different cases. So here's the statement. So you fix a tame symplectic 6 manifold together with a Darboux chart. Then you have an epsilon. There exists an epsilon such that if you take the two tori sitting inside this epsilon ball, then their images under the Darboux chart will still be non-equivalent. And this is what I call what I would like to call local exotic tori, because somehow you don't take so much into account the geometry of the ambient space. It's a local thing.
Sorry, Joey, can I ask a quick question?
Sure.
What do you mean by a tame symplectic manifold?
Yes. So tame, this is some condition on having an almost complex structure taming omega, such that you look at the associated you look at the associative Riemannian metric, and it should be you should have some bounds on the injectivity radius of the corresponding Riemannian metric and curvature bounds. So
Okay, so what some people call bounded geometry, I guess.
Yes, you can say bounded geometry. Mhm.
Thank you.
Yes. Okay. And the main observation to prove this theorem is that the invariant we look at, which is called the displacement energy germ, coming from the versatile deformations, which I will introduce all of that later. It doesn't change under the embedding phi, provided that you take this epsilon small enough. Okay. Are there any other questions with respect to this? Is the results? If not, I would move on to the construction. So, as I said, this is sort of inspired by the Lerchberg-Polterovich construction of the Chekhov torus, and other papers that sort of were important to me in my understanding of the thing was this Chekhov-Schlenk paper about the twist tori that I mentioned before, and sort of Auroux's point of view on the Chekhov torus. And this goes as follows. So I would like to. So my idea was to review first of all the construction in C2 of the Chekhov torus, and then this motivates sort of the construction in C3. So I would first spend some time on the definition of the classical Chekhov torus. Maybe formulated in a different language than what most people use. So I will talk about symplectic reduction and lifting curves from reduced spaces, but it's very close to those somehow to this paper here, and in some sense also to Auroux's point of view. So the Hamiltonian that I look at is this H here, which generates a Hamiltonian S1 action. So you take the norms of the components squared and take their difference, meaning that sort of in one of the planes you rotate clockwise and the other you rotate counterclockwise, and this gives you an S1 action. Then the idea is to perform symplectic reduction with respect to this S1 action, and then you'll end up with some symplectic surface. If C is not equal to 0, then the action is free and everything is nice, so you end up with a smooth symplectic quotient. But if the value you look at is 0, then so this thing is not smooth. So because it's not a regular value, and you have a fixed point at the origin. So you need to say something more in that case about what symplectic reduction means in some sense. But first, let's look at the smooth case. So if C is different from 0, you can check that the reduced space is actually a copy of C equipped with the standard symplectic structure. And you can observe that the product tori are invariant under the circle action that we're looking at, because the circle action is just some combination of rotations in the two factors. But so these standard circles in the two copies of C are invariant under this rotation. So the product tori sort of nicely project to circles in the reduced space. And it will actually be standard circles in the reduced space. So the green circle that I drew here is the image of a product torus under the reduction. On the other hand, you can sort of get back. So go the other way, you can look at the pre-image of a circle, and this will give you a Lagrangian in the space you started with, so in C2. Contained in the level set that you're looking at, but also in the ambient space, it will be a Lagrangian. So this is a nice feature of symplectic reduction, that you have some sort of correspondence between Lagrangians downstairs and Lagrangians upstairs. And now the idea would be, okay, let's use this to construct a new Lagrangian tori. Okay, so let's try. So let's take a curve here, some other curve, and look at its pre-image. But you can see that this is sort of pointless in this case, because downstairs in the reduced space, we said, well, those curves, if the area length closed would be the same, are Hamiltonian isotopic. So you cannot produce new examples in this way, because if the curves downstairs are Hamiltonian isotopic, you can show that their lifts are also Hamiltonian isotopic. So whatever you do in this reduced space by lifting curves won't work, because it will just give you something that's Hamiltonian isotopic to a product torus. Okay. But there is this strange reduced space where we have this fixed point. So in order to carry out reduction, I will just remove actually the point that's problematic, which is the fixed point of the action. And if you remove this, okay, so this is a mistake. It should be S1 here. If you remove this point, you have a nice open, smooth set on which you can reduce. And the reduced space will be a copy of the punctured plane with its standard symplectic form. So the symplectic form from C, where you just take out one point. But now your plane is punctured. Okay, so now there is something non-trivial you can do, namely, so again just the Clifford torus projects to these standard circles centered around the puncture, essentially. But now what you can do is you can look at these curves here, which do not contain the puncture. And at least for those, there is some hope that they give you a new torus, because downstairs you cannot move one into the other by Hamiltonian isotopy. Okay, and it turns out that this gives you indeed a new torus. So this, if you lift this curve here back to C2, so just look at the pre-image of the reduction map. This will give you a Chekhov torus. And this parameter A is just the area here that's enclosed. So you see that you can vary the area and get different sizes of Chekhov tori, essentially. What I'm doing here is not at all a proof that those are not Hamiltonian isotopic, right? It's just a hint that they might be. But I will discuss later how you go about proving this exoticity. Before moving on to C3, I would like to give a slightly different point of view on this. So I'd like to view this inside of in the toric picture of C2, because this Hamiltonian H is sort of, so the what do I mean by toric picture? I look at this moment map here, which projects C2 to the positive quadrant, and you can see that the fibers of this moment map are the product tori that we've discussed before, because product tori essentially come from, if you fix both of those numbers here, the set that you get is a product. And the Hamiltonian we looked at is essentially, so if I call this mu1 and this mu2, the Hamiltonian we've looked at is is a linear combination of mu1, mu2. This implies that the level sets of this Hamiltonian project to nice rays in the moment map picture. And this is sort of a general principle. So if you have a toric moment map image and you draw some segments or lines or rays with rational slope inside of them, you can sort of perform symplectic reduction on their pre-image. Okay. So this is what I tried to mention here. For example, probes. Maybe you're aware of this method by McDuff to displace toric fibers, which is called probes. It would be a special case of this sort of principle that you have this correspondence. And you see, so what is the relationship between H, the Hamiltonian H, and those segments? Well, H you obtain by looking at you take the orthogonal complement essentially to the rays, and they define some direction in the torus, and the S1 or the circle that we were interested in is a subcircle of the torus of the T2 action generated by this like the toric T2 action. And the Hamiltonian is just obtained by projecting to this orthogonal direction, essentially. So there's some sort of duality between choosing a Hamiltonian and choosing sort of line segments inside of the moment map image. I'm telling you all of this because this is how it works or this is how I view things, at least in C3. So let's move on to the construction in C3. So we will perform symplectic reduction on segments with in direction minus k11. And I drew some examples here in this, or I tried to draw some examples here in this picture. So this is the positive orthant in R3. Which is the moment map image of C3. And I drew the segments in these directions here, passing through 1, 1, 1, just to illustrate. And so you get this bunch of rays, depending on K, it's either a ray or a segment, because you may, so the first two go off to infinity here, and the others hit one of the boundaries of the positive orthant. And associated to these segments, you have a symplectic reduction by a T2 action. Okay, and the T2 action is again by the same principle. The T2 you would obtain by taking an orthogonal plane to the direction that you chose. So if you're taking this K minus 1, for example, you would take a plane here. Sort of hard to draw, but you would take a plane orthogonal to this direction. This plane defines somehow naturally a T2 inside of the T3 acting torically on R6 or on C3. And now we play the same game. So we look at the reduced spaces. And so for the first three values, so for K minus 1, K0, and K1, it's a bit different. So let me just, for simplicity in this talk, let me just fix K bigger or equal to 2. Then we get some orbifold reduced spaces with one puncture. And so it's what I tried to draw here, essentially. This is supposed to be the reduced space. The puncture comes from the fact that if you look over this point here, for example, the corresponding fiber of the moment map is just a copy of S1. But you have a T2 action, so there must be some S1 stabilizer somewhere. And so we take out this copy of S1 and do reduction of the complement as we did before. This produces this puncture. And on the other end of the segment, you also have a non-trivial stabilizer, but at this time it's in a finite subgroup of T2. So you will be producing an orbifold point in the reduced space. And as before, the product tori. So let's imagine that I'm looking at a product tori sitting on this blue segment here for k equal to 3, and that the space that I drew, this teardrop, is sort of the reduced space associated to this blue segment. Then the product tori are again invariant, and they will project to nice circles on this in this reduced space, which comes sort of as level sets over certain height functions. So if you write things out carefully, you see that there's still some residual sort of circle action on the reduced space in some sense, and generated by some height function, and the product tori project to levels of this height function essentially. And again, so what's the only non-trivial thing we can do? The only non-trivial thing we can do is take a circle that does not. So you see that these green circles, they're disks. You have one disk containing the orbifold point, one disk containing the puncture. And for the other thing you can do is you can take a circle where one disk contains neither puncture nor orbifold point, and the other contains both. Okay, so this is another choice of circles. And if you lift them, if you look at their pre-image under the reduction map, they give you Lagrangian tori. And those are the epsilon k tori that I want to define. Okay, so they appear as these lifts. And k is the parameter for the different families of tori, is really this the slope of the sort of segment on which we do the reduction. So another thing, so I told you that they come in 2 parameter families, and you can see the 2 parameters here, because so one of the parameters will just be the area enclosed by the curve, like the area of the disk that doesn't contain the 2 special points. And the other parameter comes from, you can sort of slide these segments in the 1 parameter family sort of along the x-axis here to get the other parameter of the family. Right. So this is the construction. Maybe it was a bit fast. So are there questions about this? One thing I should say probably is that as in the case before, there's another way in which you can move the segments. Then you could move them inside the interior of so that their sort of endpoint lies in the interior of a facet of this positive orthant. But then what happens is the puncture will disappear as before. Oh, sorry, I shouldn't have erased the whole thing. Just the puncture here will disappear. And then you can see that again, the red curves become Hamiltonian isotopic to one of the green curves. So if you try to push the segment in the interior, then you cannot expect the tori to be exotic. But this is actually important. This will come up in the distinguishing the tori. So let's move on to trying to distinguish them. And for this, I will talk a bit about this versatile deformation story. So as I mentioned, this was invented sort of by Chekhanov in '96. And there are relatively few papers making use of this technique. Two of them are written by Chekhanov and Schlenk. One of them is this twist tori paper that I mentioned before. The other one studies embeddings of product tori under Dabu embeddings. And then I also wrote another paper on another topic where I heavily use versatile deformations. Yeah, so funnily enough, I gave a few years back, I gave a 20-minute, one of those 20 minutes talk about this topic. So let me just quickly recall what the displacement energy is. So it's like a quantitative version essentially of displaceability. So you can ask, is the Lagrangian displaceable from itself by Hamiltonian isotopy? Yes, no. So that's a qualitative statement somehow. And if it is displaceable, you can ask, how small can I make the Hofer norm of the displacing Hamiltonian? And this number is the displacement energy. And we set it equal to infinity if we're dealing with a non-displaceable Lagrangian. And in an example, or examples of this would be, so the examples we've already encountered for just the standard circles in the plane, it would just be the area the circle encloses. And for the product tori, it would be the minimum of all areas of the circles. You can sort of easily convince yourself that this should be an upper bound. So in the product case, this should be an upper bound because you have those this product of these circles. It's enough to displace one of the circles from itself to displace the whole product. So if you want to minimize the Hofer norm, you will of course choose the smallest one of the circles to displace, right? So you will maybe displace this one, and then the other coordinates act by the identity. So this gives you an upper bound, and the lower bound is sort of the symplectically hard direction where you don't. It's not enough to just write down some Hamiltonian. You need to use some machinery. And the standard result is that's sort of used for to compute displacement energies of Lagrangians, is another theorem by Chekhanov, namely, which gives you a lower bound on the displacement energy. Namely, you fix an almost complex structure J, then your displacement energy will be bounded from below by the minimum of two quantities. One of them is the minimal area of non-trivial J-homorphic curves in the space, and the other one is the minimal area of J-homorphic disks with boundary on L. And the claim is that whichever J taming omega you take, this will give you a lower bound. And you can see that it works to prove the claim in these examples, because if you take the standard holomorphic structure on Cn, you can see the disks sort of in the respective components and prove that there are no others. And just the smallest one will be the minimal one, giving you sort of this equality here. And yeah, so I will use this theorem will come up again. And now you can ask, okay, so now we have this, so this displacement energy is a nice symplectic invariant of Lagrangians. So you can ask, can I use this to distinguish the Clifford tori, Chekhov tori from Clifford tori? And the immediate answer is no, because they have the same, turn out to have the same displacement energy. But still, you can do something, and this is where the versatile deformations come in. So you can sort of notice that as a function on the space of Lagrangians, the displacement energy behaves differently in a small neighborhood of the Clifford torus, and then in a small neighborhood of the Chekhov torus. And this is really the idea behind versatile deformations. So you could take other invariants. Okay, you could take other invariants of Lagrangian submanifolds, but here we stick to displacement energy. So more precisely, what do I mean? I mean, this is very vague what I wrote here. So let's be a bit more precise. So let's take a compact Lagrangian, and you have this Weinstein neighborhood theorem, which tells you that if you do C1 small perturbations of the Lagrangian, then so C1 close Lagrangian submanifolds, they will appear as graphs of closed one forms over L in this Weinstein chart. So this means that small Lagrangian perturbations are closed one forms, but we're not interested in all of the nearby Lagrangians. We're only interested in them up to Hamiltonian isotopies. So this equivalence relation here is Hamiltonian isotopies supported in a Weinstein chart. But Hamiltonian isotopies of those graphs of closed one forms correspond to adding exact one forms. And so what this means is that if we take this quotient, we end up with a pretty small space that has a nice description. I mean, finite dimensional space of sort of equivalence classes of Lagrangians, because you're dividing out closed one forms on L by exact one forms on L. So the RAM tells you that this is will essentially be the first cohomology. So so you have a nice finite dimensional description of the neighbors of L. And then you can define a function. So then you have this displacement energy, which you can apply to those Lagrangians in this neighborhood. And this gives you a function defined on this U, so on this neighborhood. And it turns out that if you take the germ of this function that you get, you will get an invariant of the Lagrangian in question. So somehow the way in which displacement energy changes when you move in a small neighborhood is an invariant of the Lagrangian you're looking at. And so this is what I would call the displacement energy germ, denoted by a fancy capital E of L, because it's a sort of an invariant of the L the Lagrangian that you're looking at. And it's a symplectic invariant in the following sense. So you only need to take into account take phi as symplectic morphism, and you take into account how phi acts on the first cohomology of the Lagrangian, and sort of this will sort of intertwine the two displacement energy terms. And this distinguishes, the claim is this distinguishes the Chekhanov torus from the product tori, and it distinguishes the examples that I've introduced. This epsilon k says that they are all they're all different once you computed this invariant. So for example, if you choose an appropriate basis, so for the Clifford torus, you'll have that the first cohomology is just isomorphic to R2, of course. And if you pick an appropriate basis of this cohomology, you will see that this germ is A plus the minimum of B1 and B2, which follows from the displacement energy computation for product tori that I gave before, because the versatile deformation of a Clifford torus is just varying sort of the two parameters inside of the family of product tori. So you have two parameters for the product tori, and these nicely coincide with the two parameters in cohomology essentially. And if you go through computation for the Chekhanov torus, you find the following displacement energy germ. And these two functions are not related by a change of basis essentially in the first cohomology. One is the minimum of two things, and one is just the other function is just projection to a component essentially. So you cannot make a change of base to get one of these functions to the other. And this as a corollary you obtain that the Chekhanov torus is exotic. And so I don't want to do the details of this computation. Here's the sort of this is where the work is hidden in some sense, but I would just like to make a small remark. So we can actually understand the versatile deformation of the Chekhanov torus pretty well with the construction that I gave before. So as it turns out, let's look at this neighborhood. Let's look at this neighborhood in the first cohomology. So since this is R2, you can think of a neighborhood of the origin in R2. And the Chekhanov torus, it appears in a one-parameter family, and if you do small perturbations of one of the Chekhanov tori in one of the directions, you'll stay in the realm of Chekhanov tori. So you get an array of Chekhanov tori. But if you move off of this one-dimensional segment or one-dimensional family, the other neighboring tori are not exotic anymore. So they are they suddenly become Hamiltonian isotopic to certain product tori. And we can actually see this because, or let me mention this remark later, but so why, how can we see this? Well, one of the parameters, so let's go back to this reduction picture of the, or symplectic reduction way of constructing the Chekhanov torus. One of the parameters in the versatile deformation is just the area parameter here. So, and if you vary the area of the curve, you'll move along this, you'll essentially move along this ray here in the family of Chekhanov tori. But if you vary if you sort of perturb the Chekhanov torus in a complementary direction, you'll move it into one of the neighboring reduced spaces. But the neighboring reduced spaces, as we said, they don't have the puncture anymore. So the curve becomes Hamiltonian isotopic to one of the standard circles. And so the corresponding perturbation of the Chekhanov torus, or the formation of the Chekhanov torus, becomes Hamiltonian isotopic to one of the product tori. And you can compute which one. You can explicitly say, if I perturb the Chekhanov torus in this way, I end up with this product torus. And this is extremely useful because of this remark here. Actually, we don't need to compute. We don't need to compute for this argument any new displacement energies, because it's enough to know what this invariant looks like on the green set. You don't need to know it everywhere to make the distinction between the two. And away from this red segment, since you are Hamiltonian isotopic to a product torus, just need to identify which one, and then you get the displacement energy for free. So it's sort of a lazy way to distinguish the two, because you just need to know displacement energy of product tori in the end. Right. Okay. I was pretty slow, but let me just say the same principle applies to those epsilon k tori, because it will look the same. So since we are in dimension 6, we have a 3-dimensional sort of family of tori in the versal deformation, and the epsilon q, I keep saying q, I don't know why, the epsilon k appear as a 2-parametric subfamily. So they are sitting inside here somewhere. And away from this 2-parametric family, it's again something that's Hamiltonian isotopic to product tori. So again, you get away with just knowing displacement energy of product tori and identifying which versal deformation corresponds to which product toris. And this is related to this fact that I mentioned before. If you take the segment on which you do the reduction and slightly move it into the interior, the puncture again goes away, and you again have this Hamiltonian isotopy moving it to standard to product toris. And if you go through this whole story, then you come up with a formula. So then you find out that the displacement energy germ in an appropriate basis. And I used X, Y, and Z instead of B1, B2, B3. So let's put them here. This displacement energy germ will have this form here, where this is for the monotone case and this is for the non-monotone case. And as it turns out, you can prove that there is no change of basis in homology mapping this function for a fixed k to this function for another k prime. So there's no such matrix mapping this invariant for k to this invariant for k prime. Which essentially boils down to some kind of determinant computation of, this is a minimum over 3 linear functionals, and you can take its determinant, there will be an invariant, and it will grow with k essentially. Okay, so I have very little time left to get to the embeddings. Let me just try to say the main points, and then I will stop. The main point you want to have is that if you have such a Darboux chart, you don't want the displacement energy to change from looking at tori inside of the ball and then moving it into tail manifold, you want the displacement energy to stay the same. And if you take epsilon small enough, then first of all, you can make the displacement. You can displace the torus inside of the ball with the same energy, meaning that you don't need the ambient space to displace. And for this, you need to take epsilon smaller than r over 2. And for the other direction, so this gives you an upper bound on the displacement energy in the ambient space. And for the lower bound, you need to use this Chekhanov's theorem. And you would like for the minimal, so in C3, it's the sort of minimal disk which determines the displacement energy. And you would still like this minimal disk to be equal to the displacement energy. So you need to take into account the J curves in the ambient space. And this is done by taking epsilon smaller than the smallest J curve in XJ. So you fix a J, which is a standard inside the double ball, and you extend it somehow. And so this, if you take epsilon smaller than this thing here, this quantity here, then in Chekhanov's theorem, it tells you that the J curves, the absolute J curves, which are not the relative ones, don't interfere with your bound, and then you end up sort of only needing to control the J disks. And the J disks inside of the ball, you know them very well, because on the ball you take the standard complex structure. And in order to say that the minimal disk cannot sort of interact with the ambient space, I use some proposition by Chekhanov and Schlenk, which tells you that if your disk sort of were to move outside of the ball, then you have some kind of buffer zone here where it needs to accumulate area. And the area you accumulate there will be bigger than the one of the minimal disk. So the minimal disk inside of the ball is still sort of minimal disk if you look at the whole ambient space. And then you get the other direction of the displacement energy, essentially, the other inequality. And I am out of time, so I will skip all of this and just thank you for your attention.
Thank you very much, Joé. Are there any questions?
Hi.
Hi.
Hi, Joe. Here's Renato Viana. So yeah, it's nice. I have some comments to do some questions. Well, the first comment, yes, you did for the monotone case, you did recover. Probably you did recover the Nice tori. You did. One can say that we do recover the same potential of him.
Okay.
And I thought a little bit. So
are you're saying it's probably the same as Denise?
No, yeah. Well, I'm saying it. Well, yeah, that the torus is probably the same of Denise. We have studied actually, me and Jeff Hicks and Dimitri, we view it in a slightly different way. I mean, we kind of like, we figured that out and we leave it because we got the Nice tori. We haven't thought as smart as you to first look to the non-monotone one and also to think about the displacement energy. Probably if you just look to minimal area holomorphic disks, you don't get enough information. But really using Chekhov's idea of displacement energy, that was something that haven't crossed our mind. Can you go to the picture where you have the moment polytope
in the construct? Yes, sure.
three? Yes.
This one?
Yes.
Oh, by now it's pretty messed up, but okay, yeah.
Yeah. But anyway, the way we think is slightly different. Instead of doing this T2 reduction, we do like an S1 reduction. You think that you can take the plane that
there's a plane containing all of those. Yes.
Yeah, there's a plane. The planes contain all of them. We don't care what happens here, but if you see what happens in the intersection of the bottom is like a Delzan. Is like a Delzan corner. So if you do reduction, you do get some local neighborhood of C2, and then you can do mutation there on DC2 from Clifford to Chekhov and lift it up, and this will recover the same tori as yours.
Probably is like one of those. Probably for one of the K. You get
no, you take these different slopes. You take these different slopes. Another way to see that, which is probably easier, and it's how we know that this has the same.
But are you saying you take planes of different slopes?
Yes. But keeping the corner with the thing that to intersect those on. So
right. So I don't understand which planes you mean. So this plane here would contain all of the blue.
No. The other one.
Okay.
A plane that would contain it probably be orthogonal to that vector that you wrote over there on Z3. Instead of probably not that vector, but whatever, something that looks like that would be orthogonal to. So the one there would be one parallel like this, and the vertical slope would be increasing symmetrically. So it's probably like 1 kk or something like that. Orthogonal to 1 kk.
Yeah, I see.
Probably something like that.
Okay.
And then you, instead of thinking of reducing to T2, it's like reducing S1 and then going in C2 from Clifford to Chekhov.
I see what you mean. Yes, okay. This will give the same ones. Yes. This will give the same ones.
But the way one can recover the superpotential over these blue lines that you drew going to the edge, you can get a Lagrangian disk.
Yes.
You can get a Lagrangian disk. And then you can perform. So the essential result will be equivalent of performing Pascal-Tonkov mutations
on the
with respect to that Lagrangian disk. Yes.
That's interesting. That's very nice.
Yes. So these are different ways of seeing it. But funny enough, we haven't pursued this direction. But now that you drew that, I just came to my mind. You can do this. You can. We like to think in some sort of tongue mutations, as if we would take a tongue out of the edge and mutate through the torus. It's something weird, sort of getting thinking about singular fibrations that me and Dimitri sometimes like to think about. But you can. We haven't never analyzed what happens, and you can do with this one, besides the one with slope k equals -1, which is a little bit different, the local situation there.
Yes,
but the ones
you hit the vertex,
the ones with the other slopes, you can do. You can perform this mutation with respect to one edge, and then you can still perform mutations with respect to the other edges.
Yes, I'm very curious about this.
Families. We haven't thought about that. We haven't really studied much that see how the superpotential change, but would give extra more families than
Yeah, that would be very, yes, it would be very
then,
nice. It's yeah.
than
Yes.
you found or Denise found. And of
Oh.
course, with your method, you could also look at the non-monotone versions of these sort of mutations and even increase the number of exotic tori and exotic
Right.
non-monotone tori you find
Yes.
In this space.
Mm.
Yeah.
Yeah, that would be a nice direction to go into. Yeah, I some version of this I would have mentioned in the further things I would like to study. Like,
Yeah.
you can think of, you probably also thought of this as some kind of analog of the ATFs in some sense. Like you can
Yes. That's
try to construct like a fibration where this is a fiber, that this is a fiber of, and so on. Yeah.
I guess we should schedule some. I can talk in more details to you some other day.
Yeah, that would be nice. Yes, that would
Yeah.
be very nice.
Yeah, but
That sounds good.
and probably we should get involved Jeff Hicks as well, because he was someone who had these clever ideas, and we somehow stopped thinking about that once we realized, oh, as of now we just recovered the Nistori. So, but with your perspective, I guess we could develop it further. It would be for the development. We can leave it to you, or but we could discuss it more.
Yeah, no, that sounds good. Yes.
Yeah, that's great. Okay.
That's good. Are there any further questions? If there are no further questions, maybe we thank Joé again for his beautiful talk. So thank you.
Thank you.